Welcome back. This is segment 2 of section 1.4. And as you may recall, I had mentioned that section 1.4 has a number of sort of like grab bag topics. It isn't real cohesive. Um, but what I want to do now is I want to develop the so-called Pythagorean identities, which are together with the other fundamental. It is a classified as a fundamental. There's actually three of them, but it's classified as its own group of fundamental identities. But it kind of allows us to now create this connection between all of the trig functions without that we don't necessarily have to appeal to the definition, which is to find a point with a coordinate and figure out all this R business, because we can now just use algebraic techniques to find the values. So what I'm going to do at this point is I'm going to introduce the three. Well, I'm going to prove them basically from some definitions, the three trigonometric identities, and then I'm going to show you how to use them to solve some basic kinds of problems. Well, I probably won't have. We'll probably end up with 3 segments out of this section, and let's just see how far we get. So let me kick it over here. I'm just gonna continue on the page that I was already on, so that you don't end up with a bunch of blank space if you're printing these off. So this was on page 2, section 1.4. So let me just remind you that for the calculation of the value of R, we had this equation where it's R equal the square root of x squared plus y squared, right? You remember this? Well, this is equivalent to R squared equal x squared plus y squared, okay? Now, what I'd like to do is I'd like to take this equation, and I'm going to do a couple things. First I'm going to say, okay, let's divide all terms by R squared, okay? So when I do that, and I'll do a little bit of rearrangement because I wanted to come out in a certain particular way. So I've got y squared over R squared plus x squared over R squared is equal to R squared over R squared, right? Now, R squared over R is a non-zero, is non-negative. Well, it's a positive number, so this is going to be defined for all values of x, y, and r. So we don't need to worry about that too much. But notice this is just 1, and this right here happens to be, if we do a little bit of switcheroo here, y over r squared plus x over r squared. It's like I'm factoring out the square term, doing a little bit of cancellation, and this right here is the definition of the sine function. Okay, so let me just pause just for a second and talk about notation. So when you and this is and maybe I'll just go ahead and do it here, and then you'll see it. So for some angle that's associated with these coordinates x, y, and r, this is the sine function squared plus the cosine function squared. And so I'm being real careful with the parentheses so you see what happens. So if you knew the value of sine, you would then square it. It is not the angle squared or some weird thing like that, because sometimes that's what people want to do. Now, to eliminate the number of parentheses that are used in mathematical notation, you're always wanting to kind of reduce the superfluous symbols and jots and dots and lines and everything else. So what mathematicians do is, if you have a trig function that is then raised to a power, rather than putting these parentheses here, it gets inserted right after the name of the function. So the shorthand for that is sine squared of theta plus cosine squared of theta. These mean exactly the same thing, but this is a little bit of a notational shorthand. Now, this is why I said from the very beginning to be really careful about making sure that you always put the argument inside of parentheses, because now if you aren't doing that, this can start to look like sine of 2 times theta, right? Which is a totally different thing. Sine of 2 theta is hardly ever equal to sine squared of theta. I mean, it can be, but it's a rarity. So anyways, so there's a notational issue, but then what we have here is what is called, generally referred to as the first Pythagorean identity. Okay? And it is incredibly useful. If you know what sine is, you can now find cosine, provided you have a quadrant. So let me develop the other two, which do not take a whole lot of time because it's a very similar idea. We just start with we divide by a different number. Page 3 now. So again, starting with a rearrangement. Let's see, let's do the one with tangent. So I want, yeah. So we had y squared plus x squared equal to r squared. Now divide by x squared. Now this is not defined for every value because you can't, when you try to divide both sides of an equation by 0, you end up with a mathematical bit of nonsense. So like with our other identities, you just have to be careful and say they're always true provided that the individual functions are defined. So there's certain angles where it's not going to work right, and that's okay, but for any other angle, it'll be fine. So when I divide everything by x squared, what I'm going to get, and I'll simplify this a little bit, is I got y over x, quantity squared, plus 1, because it's going to be x squared over x squared, is equal to r over x, quantity squared. So I skipped a couple steps there, but the same steps that we did before. Well, this right here is tangent squared, plus 1, and this right here is secant squared. So our second Pythagorean identity is tangent squared of theta plus 1 is equal to secant squared of theta. And this is the so-called second Pythagorean identity. The last one, as you can imagine, works very, very similarly. I'm going to start with a version of this. I'm just going to interchange x with y. There are certain ways that I do them just so I remember them. So x squared plus y squared equals r squared. And this time, rather than dividing by r squared or x squared, I'm going to divide by y squared. Just like before, this ends up with x over y quantity squared plus 1 equal to r over y quantity squared. And again, this is the definition of cotangent squared. This is the definition of cosecant squared. And so we end up with cotangent squared of theta plus 1 is equal to cosecant squared of theta. And this is the so-called third Pythagorean identity. All right, so why did we do all this? Well, it's because we can now use these without reference to particular points. We can now take pretty much any value of a trig function and find any other trig function's value for the same angle. So let me just give you an example of what I'm talking about. Let's try to work a problem here. Let's say, for example, there are two things you need to know. You either need to know a trig value and the quadrant that the angle lies in, or you need to know a trig value and the SIGN of another one, because that allows you to figure out the quadrant. So let's start with the easy problem, which is where we're told the quadrant and the value, and try to find the other ones. So let sine of theta equal -1/2. So the only place where this can happen is an angle that's either in quadrant 3 or quadrant 4. let's just say theta is in quadrant 3. And we don't need to find them all, but I mean, we might as well, since it's the first time we've done it. So find cosine of theta, etc. So find them all, okay? Now, what we would have done before is maybe go, okay, well, this is, there's maybe a point on that ray. We could have a y value of -1 and an r value of 2, and off we go to the races. And then we find the r value, substitute all that in, but we want to be able to use the formulas that we've developed. So first off, there's an easy one, which is that cosecant of theta is just the reciprocal of 1 over of sine. So we're now using the identities to find values. So this is 1 over 1 -1/2, which just happens to equal -2. Okay, so what about cosine? Well, let's go back to the first Pythagorean identity, which says sine squared of theta plus cosine squared of theta is equal to 1. Now, what I want to do is I want to solve for cosine. So I would isolate cosine. So cosine squared is equal to 1 minus sine squared theta. I'm using algebra at this point. I'm not doing very much arithmetic. And then now I have something that I want that's squared equal to something over here. So I might want to say take square root of both sides, right? That's a common tactic when you have something squared but you want the thing. Now you have to say this with me while you're watching this video, because when you take the square root of both sides, you have to always include a plus or minus, right? Plus or minus, plus or minus. So when I take the square root of both sides, cosine of theta pops out over here, but we have a plus or minus the square root of 1 minus sine squared of theta. Okay? This is two possible answers. Two possible answers. How do we figure out which one it is? Well, we know what quadrant it's in. Quadrant 3. Remember the mnemonic, which is that all students take classes. In quadrant 3, that's take. So tangent and cotangent are positive. Everything else is negative. So from this information, we establish that this has to be the positive branch, okay? Sometimes it's negative, it just depends on the quadrant. So cosine of theta, because we know the quadrant, is the positive square root of 1 minus sine squared of theta. Okay, so once we have this equation, we can substitute in the value for sine and find cosine. And I'll do that here on the next page. At 1.4, page number 4. Okay, so just to repeat it here, cosine of theta is equal to the positive square root 1 minus sine squared of theta. Now, remember, sine of theta is -1/2. So this is the positive square root of 1 minus -1/2 squared. Be careful with these parentheses because you'll mess up the SIGNs if you're not careful. When you square a -1/2, you get 1/4. So I'm going to kind of do a little bit of fractional magic in here. 4/4 is 1 minus 1/4, which is equal to positive square root of 3/4. Now this is not simplified. There's plenty of reasons why. So I'll just do the chain of what you would do. When you have a fraction, you break them up. So this is going to be the positive square root of 3 over the square root of 4. And this is not simplified. We have both a fraction in the denominator, and this happens to also be a perfect square. So this becomes positive square root of 3 over 2. And we've actually seen this number before. So now you have sine and cosine. Once you have one of those kinds of pairs, the rest of them become pretty easy. So going to the next one in the chain is tangent of theta. Well, I guess we could do secant. We'll come back to that. Tangent of theta is sine of theta over cosine of theta. Again, I want to use fundamental identities to do this. So that's negative 1/2 divided by square root of 3 over 2, which happens to equal negative 1 over square root of 3, which simplifies to negative root 3 over 3. Okay? So I've got, now I've got sine, cosine, tangent, and also cosecant. Maybe we come back for secant. Secant of theta is equal to 1 over cosecant, or sorry, cosine of theta. Here's the cosine of theta, positive root 3 over 2. So this is, we've done this one before, so I'm not going to waste too much time on it. It'll be positive 2 root 3 over 3. And then finally, cotangent of theta is the reciprocal of tangent of theta, which this might be the best expression. Just flip this upside down, will be negative square root of 3. So to summarize then, sine of theta equals negative 1/2. Cosecant of theta is equal to negative 2. Cosine of theta equal to positive root 3 over 2. Secant of theta is equal to positive 2 root 3 over 3. Tangent of theta is equal to negative root 3 over 3. And cotangent of theta equal to negative root 3. Okay, so I think sometimes these problems with all the explanation that I have in them take a little bit of time. So I'm going to come back in a third segment and do another problem similar, not exactly the same, but essentially the same kind of problem. And then there's one other kind of sort of weird thing that crops up in this in this section that that I think I want to just sort of point out. It's sort of a weird thing that it seems completely out of place in this section, but since it's there, I always get questions about it. So I will see you again in probably the third and final segment.